So thanks for this introduction, and thanks for the organizers to give me the opportunity to present this talk, and I will give it in English for English speakers. So this presentation is about a comparison of different chemometrics methods for the spectroscopic monitoring of chemical compounds in the context of pharmaceutical processes. So in the pharmaceutical industry, we often use methods such as the mini-infrared spectroscopy and the high-pressure liquid chromatography to monitor chemical reactions. And so, for example, with mini-infrared spectroscopy, we get spectra which are recorded over the time of the reaction, like continuously. And HPLC samples are taken over time of the reactions. Those samples are then separated by chromatography and quantified. The molecules are quantified by UV. And then, for example, on this plot, we can see that at 4 time points over 21 hours, the product was increasing and the reactant was decreasing. So actually the context of this work was to help some scientists and the chemists at Janssen to provide them some statistical tools to better understand chemical reaction kinetics and also to have better control of the product's quality. And in this presentation, I will actually make a comparison of different chemometrics methods which have been explained like yesterday and also today to answer 2 objectives, which are first to visualize and interpret chemical reactions using dimension reduction methods such as PCA, MCR, or NMF. And the second objective, which will be to predict chemical concentrations over time using calibration methods combining PCA, MCR, and NMF scores and PLS. So for the first objective, let's consider a single batch which is only monitored by spectroscopy. So we will get spectral data, and we would like to, only from those spectral data, to visualize the evolution of the main chemical compounds during the process over the time of the reaction, and also to have a look at the most influential spectroscopic variables. Or if you have recorded multiple batches, multiple reactions, we would like only from the spectral data to look on the same space, the evolution of the same compound and compare it for different reactions, and also, again, looking at the spectroscopic variables of influence. For the second objective, which is to predict chemical concentration, imagine that we have a single batch monitored by infrared spectroscopy and also HPLC. We would like, from those 2 types of data, to build a calibration model and then getting predictions of the main chemical compounds over the time of the reaction, but also getting those concentrations at all the time, which were not recorded by HPLC, for example. So making some interpolations. And if you have like multiple batches, historical batches, we would like from those 2 types of data, HPLC and spectroscopy, to build a model. And when a new batch is recorded, processed, we would like to apply the calibration model on only the spectral data to get the predictions of the main chemical compounds in the reaction. So an overview of this presentation, I will first start with the data sets and statistical methods which have been used, then answering the first objective, which is to visualize and interpret chemical reactions, and then the second objective, which is to predict chemical concentrations over the time. So let's start with the data and the statistical methods. So the data that I've been using in this project consists actually of 11 batches, which were monitored by infrared spectroscopy and HPLC, and the idea was to synthesize the same compound, a pharmaceutical compound. So we have first a spectral matrix with the 11 batches, and all those batches have been recorded by spectroscopy over 21 hours. And we can put actually all the spectra in rows. So we have a matrix of more than 6,000 rows and 200 columns around for the number of spectroscopic variables. We also have an HPLC matrix, also corresponding to the 11 reactions. And we have 2 columns because 2 compounds were quantified by HPLC. The final product and the reactant of the reaction at 4 time points, and then the dimensions are 42 by 2. So the first method which will be used is the principal component analysis, and in this context the idea will be to actually decompose a spectral matrix called X into scores called here H, which will help to follow reaction components over the time, and also loadings called in this presentation W, which will help to detect influential spectroscopic variables. I will also use 2 other methods, which have been explained already during this yesterday and today, which are non-negative matrix factorization, which is more coming from the field of signal processing, and also multivariate curve resolution from the field of chemometrics. And here, those methods will be applied also on a spectral matrix, but which has to be non-negative, which is the case with mid-infrared spectra. And the spectral matrix will be decomposed into scores and loadings, which will also be non-negative, but the number of dimensions is chosen upfront for the decomposition. And actually those 2 methods share 3 similar steps, a similar algorithm. The first step is to initialize the scores and the loadings, providing random or prior information. Then the second step is to optimize alternatively the scores and the loadings, so that the error of the model at each iteration decreases until the error of the model is sufficiently low or lower than a certain amount, and then the algorithm stops. In this project, in this work, so the way to optimize the scores and the loadings for the method MCR, I've used an alternating least square algorithm from the R package ALS. And so at each iterations, the scores and loadings where the negative elements were set to 0 for the non-negativity constraint. And for the method NMF, I've used a projected gradient algorithm from the R package HNMF. And also the negative elements were set to 0 over the iterations. Of course, for the methods like MCR, it's known that additional constraints can be used, such as unimodality or constant sum of trends. But here in this presentation, in this context, I've only used the non-negativity constraints. I've only used 2 components for the decomposition, and I've used a pure spectra of my 2 components as prior loadings. And finally, the last method is the partially square regression. And here, the idea is actually to build a calibration model from the spectra and HPLC values, and then to apply this calibration model on a new spectrum to predict new HPLC values. So, in this section, I will answer the first objective, which was to visualize and interpret chemical reactions using methods such as PCA, MCR, or NMF only on spectral data. So here we can have a look at our full spectral matrix with our 11 batches. And actually, what I can do on the spectra of each batch, I can apply the decomposition by PCA, NMF, or MCR, looking at this formula. and I will get an error of the model. I can do that for all 11 batches, and I will get a distribution of my errors. And actually, if you look at this table, what I've done was to just calculate the mean error percentages for the 11 batches by applying PCA, MCR, or NMF. And we can see that so MCR and NMF have quite similar errors, and PCA gives the lowest errors. Then in this slide, what I've done was to apply the methods PCA, MCR, and NMF only on the spectra of the reaction tree, of the batch tree. And it's interesting to compare the loadings and the scores of those different methods. So let's have a look at the loadings in PCA. The loadings in PCA, because of no constraint is applied, can be negative and positive, which is sometimes for chemists not so straightforward to interpret. And if we look at the scores in PCA of the time of the reaction, the values of the scores can also be negative, which is not straightforward for interpretation. However, if we look at the loadings in NMF and MCR, here they are really close, so we cannot really make the difference. In red for the reactant and in blue for the product, the loadings are positive, so which correspond more to the spectroscopic variables. And we can also have a look at the evolution of the scores in NMF and MCR for the reactant, in red decreasing, and the product in blue increasing. So, and all the values are positive, which is easier to follow the reaction over the time. So actually, even if PCA gives a lower error of the model during the decomposition, NMF and MCR have a big advantage because they offer more interpretability than PCA, which is interesting for the scientists and the chemists. So the last section is here to predict chemical concentrations by applying a combination of PCA, MCR, NMF, and PLS on spectral and HPLC and data. So I've used two methodologies actually to calculate the prediction errors of the models. So the first one is to apply a one-step leave one batch out PLS and using only spectral data. And the idea is actually to build a PLS model in the first step from the spectral data and HPLC data from all the batches minus one. So 10 batches. And then applying the calibration model on the missing batch. And then I will get prediction of my HPLC concentrations that I can compare to real observed HPLC concentrations, and I can calculate the root mean square error prediction. And I can do that for all the 11 batches. So the idea here would be to build a calibration model from historical batches, and when a new batch is coming, to apply the calibration model on this new batch. I can do a similar methodology, but actually building a calibration model from the scores of PCA, MCR, or NMF. And here, the idea is to, in the first step, to get the scores by applying MCR, NMF, or PCA on all my spectral data from all the batches except one. Then I use the model on the missing batch, and I'm getting the scores for the missing batch. In the second step, I can build a calibration model between my HPLC values and my scores for the 10 batches, applying this calibration model on the scores of the 11 batches, to get predicted HPLC values, which can be compared to real observed HPLC values, and I can calculate the root mean square error prediction and repeat that for all the 11 batches, and I will get a distribution of root mean square error predictions. So the results of those two methodologies to calculate prediction errors can be summarized actually in this table, where you can see the mean root mean square error prediction for all the 11 batches. For simple PLS with 2 and 7 variables, and for the scores of PCA, MCR, and NMF, yes, followed by PLS. We can see actually that methods PCA, MCR, and NMF building calibration model from their scores give similar errors from 5.7 to 7, knowing that HPLC values can range from 0 to 100. It's around 6-7% of error. But the lowest error predictions are still obtained with PLS, especially with the optimum with 7 variables. So the PLS method stays the reference method for building calibration models. And here, on this last slide, I've applied the method PLS, PCA followed by PLS, MCR, and NMF followed by PLS only on the batch 1. And for example, we can look at the predictions over the time of the reaction for the product increasing and the reactant decreasing. The points are the real observed HPLC values, and the lines are the predicted values. And we can see, especially for PLS, that the predictions are quite close to HPLC values, and hopefully the other methods give similar trends, even if errors are a bit higher, maybe with MCR. So, in conclusion, this presentation was about a comparison of different chemometrics methods to help chemists and scientists at Janssen to better understand chemical reactions. The first objective was to visualize and interpret chemical reactions, and we have seen that methods such as NMF and MCR, because of the non-negativity constraint, are more interpretable than PCA. And for the second objective, which was to predict chemical concentrations, PCA, NMF, and MCR give similar prediction errors, but still the PLS method remains the reference calibration method. And those methodologies could be, for example, used in perspective for quality control or real-time monitoring. So thank you all for your attention, and if you have any question, I would be glad to answer.
Thank you for the presentation. Regarding your last point on the online prediction of the quality of your batch process, the approach you follow allows you to predict the output variable at that particular time. But what happens if your point is to endpoint prediction? I mean, predicting the ending, the quality. Have you thought about how to deal with this problem? Because probably the way you arrange your data matrix doesn't allow to do that.
So your question is to know how those methodologies could be applied to know the end of the reaction?
Yeah, even at the very beginning of the batch, you can predict how well is going to be the output of your batch, the endpoint, for any quality characteristics you have.
To know the endpoint of the reaction using those methods, using PLS, I think that you should know the final concentration of your product, and when those concentrations would be reached at a sufficient amount of time, we could consider, I guess, that the reaction is stable and could be stopped. And if you would like to use NMF or MCR to know the end of the reaction, I guess we should have a zone which is stable a sufficient amount of time. Does it answer your question?
Well, we can discuss later on.
Okay.
Merci beaucoup, Michel. On peut l'applaudir.